Yes, class. Am I audible to all of you? Just check.
Yes, ma'am.
All right.
Yes, ma'am.
Okay. So yes, we have to start with nucleus today. So let us quickly revise. This is a short lesson. We just need to practice certain questions from this, and we have to see some theory portions from this as well. Now, see from nuclei. This is the basics of nuclei. The meaning of nucleons, meaning of what is atomic number, meaning of what is mass number, all these values. So see, nucleons means when we collectively talk about protons and neutrons. Fine, that is what is meant by nucleons. When we specifically talk about only the number of atoms that are present, only the number of atoms which are present, then we call it as atomic number. And if we talk about protons and neutrons, means whatever content is present within the nucleus, that is known as mass number. So nucleons means protons and neutrons, and number of nucleons, that is protons and neutrons, is known as mass number. And number of protons that are present, that is known as atomic number. So these are the basic things. Now see, number of protons is denoted by capital Z. This is denoted by this capital Z, that is the atomic number. And in our numericals also, we'll be using Z only. Number of electrons and number of protons both are equal. The number of protons and number of electrons that are present both are equal. But see, if we have to find out the number of neutrons, so completely we know, no, protons plus neutrons is equal to mass number. See here, look here, in the corner of the screen, look here. So protons plus neutrons becomes the mass number. So if I have to find out number of neutrons, protons I know is Z, atomic mass number I know is A. So what will be number of neutrons? Mass number minus protons. So mass number minus protons becomes number of neutrons that is left. So A minus Z. And number of nucleons. Number of nucleons is A, that is the mass number, means number of protons plus neutrons. So number of protons Z, number of electrons Z, number of nucleons A, which is the mass number, and then we have number of neutrons, that is A minus Z. So these many things you have to remember. Note it down. Some more terms we'll see for the numericals. Just note this down. Now, see some more terms that will be used in the numericals. See, first term is isotope. Now, isotope means, so we have studied proton number and mass number. Protonic number, this is Z, that is the number of protons that are present, and mass number is represented by A. So, if values of protonic number, that is same, it remains the same, but mass number is different for two elements. For example, if I talk about all the isotopes of hydrogen, protium, deuterium, tritium, so H1, mass number for all of these that we are that we'll see is different, 1, 2, and 3, but atomic number is same, that is 1, right? So this is one example of isotopes. So you'll not be asked to directly use this and give an example, but in the numericals it might be given to you. Then next quantity, if we inter-reverse this, same A and different Z, that is same atom, same mass number, but different atomic number. So in that case, you will be having isobars. You have isobars. So best example is if you take the example of chlorine and sulfur. Approximately the mass number that chlorine and sulfur possess, it is around 37. If you choose the isotope 37 of chlorine, one isotope of chlorine that is present is Cl35 as well. So that one we won't take. But for chlorine 37 that is required, this we'll take it with sulfur. So one sulfur's protonic number, that is the atomic number, is 16 and chlorine's is 7. So different Z, but same A. You have the example of calcium and argon as well. See, argon comes prior in the periodic table, no, before calcium. So value of argon is what? Value of argon is 18, and the value of the protonic number, that is atomic number of calcium, this is 20. But both of them have the around the same mass we take, no, 40 grams. In chemistry also you must be using. So we approximately take it as 40. So this is also an example of isobar. Then we have isotones. Isotones means number of neutrons remain same. Now, how were we calculating number of neutrons? For number of neutrons, we had A minus Z. That is what we are going to write. Whatever is the mass number, we'll subtract whatever is the atomic number. So suppose chlorine, if you take 37 is its mass number, 17 is its atomic number. If you subtract 37 minus 17, you will get a number, right? That is 20. If you take this example of potassium, let me show you this example. If you take this example of potassium, so here also you have 39 as the mass number and 19 as its protonic number. So 39 minus 19, this gives you 20. So both are having A minus Z same. See, 37 was also different, 39 is different here. 17, 19, both are different. But when we subtract it, at the end we obtain 20 in both the cases. So if we are getting 20, that means both are same, having same number of neutrons. Fine. So if two elements are having same number of neutrons, we call them as isotones. Lastly, isomers. Isomers you study in chemistry, organic isomers and organic isomers that are formed. So Z also remains same. Here A also remains. Mass number, atomic number, both remain same. It's just that they have energy states different. Different formulas are also there, and their chemical structure is mainly different. So isomers are not very important to you. You just have to remember these three. These three will be needed, and their examples, because in statement-based questions also they can be asked, and they have been asked. From these three at least. So note it down with the examples. Yes, one more thing. This is the representation of chemical atom, any element that we have. So on the topmost corner, in the superscript, we write the mass number, and in the subscript lower corner, we write the protonic number. This is how we represent that. You all must be knowing it. So note it from here. Now, C class, these much data, these will be used by you because these won't be given in the question. So it's better directly remember these things because in the nucleoside questions, in the mass defect question, especially, you will be needing all of these concepts. So mass of electron, mass of proton, mass of neutron, these three you should remember, not this mass of hydrogen that you can add, and that will differ also. So mass of electron is 0.0055 AMU. Please remember it and do not round it off when you are solving, because in the options that will be given to you, all the options will be given, one with rounding off also and other one without rounding it off. So you have to choose the precise answer, so do not round it. Whenever you are getting a question from mass defect also, 0.00103, whatever decimal values are given, directly just add it or subtract it as per the question. Do not shift the last digit or round it off to make it even or so, likewise. So mass of proton, mass of electron, and mass of neutron, at least these three you should remember. Now, mass of proton is 1.0073 AMU, mass of neutron is 1.0086 AMU. So this much you have to remember. Yes, next topic is nucleus size. Just note down this, then we'll start with nucleus size. Now, see the nucleus size. So, value of nucleus size, whatever is the volume of nucleus is directly proportional to its mass number. So we consider nucleus approximately as a sphere only with radius capital R. So volume becomes 4 by 3 pi r cube. That is what is the volume of nucleus we write if we choose a sphere with a radius R. So this is directly proportional to its mass number, which we have chosen and depicted as A. So if we just focus on the things which are proportional to each other, if we eliminate all the constant terms, see 4 by 3 pi r cube, all these are just constant terms. If we just focus on the terms that are proportional to each other or are dependent on each other, so r cube is directly proportional to a. So r becomes 1 by 3, a to the power 1 by 3, or cube root of a, you can say. Now class, R naught is 1.2 into 10 to the power minus 15. R naught, this is a constant that we put in place of this proportionality sign, R naught. So value of R naught is fixed, that is 1.2 Fermi meters, and 1 Fermi meter we write it as 10 to the power minus 15 meters. Now see, if in the question, some questions are there in which it is specified whether to use 1.2 Fermi meters, or in some of the questions it is given use R naught as this much Fermi meters. So in that case, do not use this, put in the value whatever is given in the question. Otherwise, if no value is provided to you, R naught is equal to 1.2 into 10 to the power minus 15 meters. This is what you're going to substitute. It can happen in the options, you will get it in Fermi meters only. So 1 Fermi meter you can equate it to 10 to the power minus 15. So R is equal to R naught, a to the power 1 by 3. You have to utilize cube roots, you have to solve it and find. Fine. Note down this page. These values you're talking about? Okay, noted. Now class, one more concept that you have is of nuclear density. So see, nuclear density is remaining constant for every term. So you will get questions where different values will be provided to you, and ultimately you will be asked to write about nuclear density. Or it can also happen that regarding nuclear density, you will have to you'll have statement based questions where you'll be having certain statements where you have to write about what is the correct value of density, and density is depending upon which all of the quantities. So you have to remember, see, density is mass by volume, mass of nucleus by mass of volume. No need to go through the derivation, just remember this, that value of density, when ultimately we substitute all the values of density, we at the end obtain 2.3 into 10 to the power 17 kg per meter cube. This is what we obtain at the last. So if this value is given, you do not have any mass number within this, you do not have any atomic number present, you do not have the radius present within this. So if you are having such values, right, it means your density, this is totally independent on the mass number. Whatever is the size, whatever is atomic number, whatever is the mass number, this is completely independent of. So value of density that finally comes is 2.3 into 10 to the power 7 meter cube. You have to remember this value because this value can be asked to you, and one question I'll show you. See, look at this fourth question. Nuclear mass of iron 5626 is 55.85 AMU, and it says that calculate its nuclear density. Now see, you don't have to calculate anything in such types of questions. Values are given, data is provided. You do not have to worry about it. Just directly write it as 2.3 into 10 to the power 17 kg per meter. All right. And one more question. See, in this, like it was provided, take R naught. You have to find out the radius using the formula that we have studied for the nuclear volume, nuclear size one. So here it was given R naught as 1.1 Fermi meters. So here we won't take it as 1.2 Fermi meters. It would be 1.1. All right. So just to note down this part from here, not the derivation part, that is not needed, just this part from here. Question 4th, which I have shown you. Okay, I'll scroll it. This part is written, I think, by all of you. This is first one. Now see calculation of mass defect. So for mass defect, certain terms, one single formula is needed by all of you. Just understand the meaning of term. Delta M is the mass defect. Now ZMP. If I have the mass of a single proton is MP and there are Z amount of protons present, right? What is the total number of proton that you have? What are the total number of protons that you have? So total number of protons that are present is Z, that is what we have taken it as the atomic number. So total mass become, for one proton you have MP. So for Z protons that becomes ZMP. So this entirely is the mass, total mass of protons. Fine. Coming here. Total number of neutrons, A minus Z. This is how we calculated number of mass number subtracted. We have subtracted mass number and proton number. That is the atomic number. So that gave us the amount of neutrons present. So if a single neutron has mass Mn, so A minus Z amount of neutrons will give you the mass A minus Z into Mn. So this is ZMP, A minus Z Mn. Minus Mn is the entire mass of nucleus. So this formula you have to remember. This formula is sufficient. But some more things apart from this. For this formula, once you obtain the mass defect, sometimes binding energy can be asked to you to write about the binding energy, to calculate it. So whatever is mass defect, using your Einstein's equation, mc square E is equal to mc square, your energy here becomes binding energy. Mass, that is the mc, in the formula mc square we use the mass. Mass is the mass defect, and c is again speed of light. So you will take the square of speed of light, c square. Now, one thing you can do, instead of taking this as entirely c square, that is 3 into 10 to the power 8 whole square, and multiplying with whatever mass defect you have obtained, you can directly multiply this by 931 mega electron. Whatever is the mass defect obtained, no, you have obtained the mass defect, that you just multiply it with 931 mega electron volt. That will also be the same answer. It's just that you'll obtain the answer in the SI, not in the SI unit, it would be in mega electron volt. So you can solve using this also, and if it is required, you can then convert mega electron volt into normal general your joules, the way we convert electronic volts into joules. So by just putting the values of electronic charge, 1.6 into 10 to the power minus 19. So this is binding energy, how you calculate delta M multiplied by C square, or delta M multiplied by the value of 931 mega electron volt. Now, one more thing that you have, if per nucleon is mentioned to you, then divided by the mass number, because that means this entire is the mass number. One nucleon it is talking about. Per nucleon means per a protonic or a neutronic charge, right? So divided by the mass number. So you can divide this entire term by mass number, or this entire term by mass number if mass number is asked to you. Otherwise, binding energy, this is not necessary to calculate. Binding energy is calculated using this or using this, that is enough. Note this down, mass defect. This is an important topic, mass defect. Note it.
Ma'am, is the mass of the nucleus outside the bracket?
This mass of, no, this is within the bracket only. It's just that in order to differentiate A minus Z, this is mass of neutron, not nucleus. This is out of the bracket. This is mass of the entire nucleus.
Okay.
the half-life of a radioactive sample undergoing alpha decay, this is given as 1.4 into 10 to the 17 seconds. Now, if the number of nuclei in the sample is 2 into 10 to the power 21, activity of the sample is nearly. Now, we have the formula. T half is given to us. T half is given as 1.4 into 10 to the power 17 second. Now, the activity of these is lambda n, disintegration constant, and number of decay that is present. This is actually equal to, T half is equal to lambda by 0. Root 2 value, we write 0.693 by 1, by whatever is lambda's value. This is general. First, write down the general formula for it, lambda. So value of lambda from here, we get, or the entire activity of the sample that we get is 0.693 by T half. We shifted here to here. If you get the value, write the value of lambda n. T half will become 1.4 into 10 to the power 17. This will become T half. Now, number of nuclei, this is for a single sample. What is the number of nuclei present? So this becomes 2 into 10 to the power 21. N is value. So solve it. See what is the value you're getting it. Which option is correct out of this? Becquerel is the SI unit of radioactivity. No, Marita, for first one, you're right. Option A will be for this one. Here, option A is the correct answer. That is 10 to the power 4 becquerel, but not for this one. See, the formula that we use, no, remember, Marita, we had a class also on this. So same formula we are going to use. dn over dt is equal to lambda n. This is rate of change, which is which is directly proportional to number of samples that are left. Alpha, this lambda is the decay constant. This is the decay constant.
Sorry, ma'am, I had a calculation mistake. I guess it's option D.
Yes. Option B. D is right. So now see, value of R, that is the rate of the whole reaction. Rate of disintegration, basically we say this entire term is rate of disintegration. So this is equal to lambda n. Now n is equal to R divided by lambda. And I have told you the formula, no? T half-life is 0.693 divided by lambda. So put in the values of it. This becomes R by 0.693 multiplied by T half. So rate of radioactive disintegration is given as 10 to the power 10. And half-life is 2.2 into 10 to the power 9. So you just have to substitute in the values. This becomes 10 to the power 10 into 2.2 into 10 to the power 9 divided by 0.693. So this becomes equal to 3.717 into 10 to the power 19. So D option is correct. Noted? See, this question says that for a radioactive material, half-life is given as 10 minutes. If initially there are 600 number of nuclei, the time taken in minutes for the disintegration of 450 nuclei. See, after half-life, the number of nuclei that are left undecayed, we use the formula n naught by 2 to the power n. Or you can write this as n is equal to n naught half to the power n. This formula is used. All right. So initial n naught is the initial number. Initial number of nuclei, which is given initially there are 600. So n naught is given to us as 600. Now n, how much is left? How many have disintegrated? Disintegration of 450 nuclei. So how much is left? 600 minus 450. That becomes 150. So n you have, n is equal to 150. So take the ratio n by n naught is equal to half to the power n. This is the formula that we use. Now see the value of the small n. What actually is this small n? This small n is time duration that is there, divided by the half-life. This is the normal total time that we take, and small t half is the normal half-life that we take. This is what is meant by value of small n. Now see, if we substitute in here all the values, n is 150, n naught is 600, half to the power. Now see what all things are given. Half-life is given as 10. We have to find out the time taken for disintegration, total time, that is small t. So this is half-life is given as, this half-life, this is given to us as 10 minutes. This is unknown. So this becomes 1 by 4, right? This becomes 1 by 4 is equal to half to the power n. We can write it as t by 10. Now look, 1 by 4, I can write it as 1 by 2 whole square. And this also 1 by 2 to the power t by 10. So it means I can equate the powers. This and this, they can be written as equal. So t by 10 is 2, t is equal to 20 minutes. This is a very important question. This is a very basic question that is repeated a lot. So please mark it as important and note it down.
Ma'am, what is capital N?
Capital N is the number of nuclei that are left now after disintegration. This is initial number that was present. Now some must have disintegrated, like 450 has disintegrated. Now what is the number of nuclei that are left undecayed? This is capital N.
Okay, ma'am.
See, this question says that the half-life of a radioactive substance is 30 minutes. The time in minutes taken between 40% decay and 85% decay of the same radioactive substance. See, half-life is actually directly proportional to log n naught by n. When we say half-life is left, we are going to use the previous formula only, the formula that we have been studying, not this one. We'll use the previous formula only. So if it is saying 40% decay has occurred, how much will be left? 60%. So N1 will become 0.6 of N naught, 60% of initial. And if it is saying 85% decay has occurred, so N2 will become means 15% is left. So 0.15 N naught. Now take up their ratios. N1 by N, or just let's take it as N2 by N. N2 by N1, this is 0.15 N naught by 0.60 N naught. So 1 by 4 here is also left. That is 1 by 2 whole square. Small n we have, it as 2. How did we write the formula? Time by t half. We have to find out the time taken for the whole decay. That is small t. And half-life is given to us as, I think, 30 minutes or 60 minutes? 30 minutes. So yes, small t is going to be t half into n. So 30 into 2, 60 minutes. So which option? D option. Fine, noted. All right, class. We'll continue semiconductors, and I think one more question I want to discuss with you from nucleus. That we'll discuss it tomorrow. So revise semiconductors and come. We'll discuss semiconductors tomorrow. Okay. Thank you so much, class.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.